Right now, as you are listening to these lines, there is a scientific instrument doing something that no other instrument in the entire history of the human species has ever been able to do. It is not located in any multi-billion-dollar observatory. It is not on any space station. It is drifting in the darkness, about 13 billion miles away from us, mounted on the body of a machine that was built before personal computers existed, before most of the scientists now analyzing its data were even born. It runs on about 4 watts of electricity. 4 watts. The little light inside your microwave oven uses more power than that, and this instrument, called PLS, plasma science, is sending back to us measurements that no model built from Earth has ever predicted accurately. Researchers at MIT, at the University of Iowa, at NASA's Jet Propulsion Laboratory no longer use the words interesting or surprising. They are using the words we were wrong. And in the coming weeks, the machine carrying this instrument will undergo the most daring test of its 49 years of operation. Stay with me. Because by the end of this video, you will understand why this old 4-watt machine, and not any multi-billion-dollar telescope, is the most precious microscope humanity has ever had. Subscribe to the channel right now if you want to hear more stories like this, because we are only just beginning. Let us go back to November 5th, 2018. In a control room at the Massachusetts Institute of Technology, John Richardson and his team were sitting in front of screens displaying real-time data from a machine 11 billion miles away from them. The spacecraft we are talking about is Voyager 2. It was drifting at a distance of 121 astronomical units from the Sun. That means it was about 121 times farther than the distance from Earth to the Sun. Light from the Sun, the light that touches your skin in just 8 minutes, takes nearly 17 hours to reach its position. And in a short span of only a few hours that day, Richardson and his team watched the plasma density around the spacecraft jump by nearly 40 times. This was not a smooth transition. This was not a gradual boundary shifting from one region to another the way models had predicted for decades. This was a wall. Across a cosmic distance so small it is almost unimaginable, the environment around Voyager 2 changed completely from the warm, tenuous solar wind to the cold, dense plasma of interstellar space. And for the first time in the entire history of our civilization, a human plasma instrument had directly measured the boundary separating the solar system from the rest of the galaxy. Not inferred from afar, not a mathematical model, not an observation through a telescope, measured directly, minute by minute, from right inside it. This is what I need you to understand so that the rest of this story makes sense. 6 years before that event, in 2012, Voyager 1 had also crossed this same boundary. But it crossed at a distance of 119 astronomical units, not 121. A difference of 2 astronomical units may sound small on a cosmic scale, but remember that number. It will come back at the end of the story. And there is one other crucial difference between the 2 crossings. Voyager 1 crossed while blind. Its plasma science instrument, the very instrument designed precisely to measure the density and temperature of the surrounding plasma, had stopped working in 1980, only 3 years after the spacecraft left Earth. Throughout the 6 years between the 2 crossings, and for the entire time from then until now, there has been only one single instrument in the whole of human civilization capable of directly measuring plasma in interstellar space. That is the PLS on Voyager 2. Voyager 1 crossed the boundary with its eyes closed. Voyager 2 crossed with its eyes open. And what it saw, what it is still seeing right now as you listen to these lines, does not match any model humanity has ever built from Earth. 7 years of analysis later, the scientific community is still trying to figure out exactly what that means. Let us begin with the spacecraft that carried the PLS there. To understand why Voyager 2 is where it is today, you need to know something that very few people know. Its flight could only happen once every 175 years. That is the rare cycle in which the 4 giant planets of the solar system align in a curve that allows a single spacecraft to fly past all of them in one mission. If NASA had missed the window in 1977, the next opportunity would not come until 2112. To grasp how long 175 years is, remember that Neptune was first discovered in 1846, and to this day, nearly 180 years later, that planet has only just completed a single orbit around the Sun. One revolution of Neptune is nearly equal to the entire lifespan of modern civilization. Voyager 2 left Cape Canaveral on August 20th, 1977, 16 days before Voyager 1, but flew a slower trajectory so it arrived at the planets later, and was therefore given the confusing name Number 2. Launching it away from Earth required a clever trick. The escape velocity from the Sun's gravity at Earth's distance is 42 kilometers per second, and the most powerful rocket of the time, the Titan 3E, could only provide an additional 10 kilometers per second. Not enough. But Earth is orbiting the Sun at 30 kilometers per second. Launching in the same direction as Earth's motion, the spacecraft borrowed that entire velocity, reaching 40 kilometers per second relative to the Sun. Then it used the gravity of each giant planet like a slingshot to borrow still more speed. Voyager 2 reached the edge of the solar system by borrowing speed from the very planets it flew past. On July 9th, 1979, it reached Jupiter, discovered the small moon Adrastea, and photographed the Great Red Spot, when that storm was still nearly twice its present size. On August 25th, 1981, it reached Saturn and recorded something strange on the moon Enceladus, smooth young plains lying next to ancient cratered terrain on the same surface. In January 1986, it reached Uranus. The planet tilted 98 degrees as if it were rolling on its side. There it discovered rings and 11 moons that were not in any catalog. On August 25th, 1989, it reached Neptune and photographed the great dark spot large enough to swallow Earth. Measured winds of 1,500 miles per hour, the fastest ever recorded on any planet in the solar system. This entire grand tour took 12 years, and to this day, nearly 4 decades later, Voyager 2 remains the only spacecraft in the entire history of humanity ever to have flown past Uranus and Neptune. No mission is currently planned to repeat this journey. Everything we know about the 2 outermost planets of the solar system comes from the brief hours when Voyager 2 flew past them nearly 40 years ago. After that final flyby, the spacecraft continued into the darkness. There were no more stops. Only distance and silence and 29 more years until it reached the true boundary of home. Inside that bubble is us, outside it is no longer us. And Voyager 2 touched that boundary, 6 years after Voyager 1, traveling in a completely different direction, carrying a plasma eye that was still alive, and this is what that eye began to detect in the 7 years after crossing. If the story had stopped at the moment of crossing, it would already have been enough to rewrite the physics textbooks. But the story did not stop there. Voyager 2 kept going, kept measuring, and for 7 years after the day it crossed the Heliopause, the PLS sent back what it was seeing, day after day, year after year. What it sent back has become one of the most uncomfortable mysteries in modern plasma physics. The plasma density in interstellar space, instead of remaining constant as all the models had predicted, is increasing. This is what I need you to understand precisely because it is very easy to confuse. This is not the 40-fold jump when Voyager 2 crossed the boundary itself, the sudden wall I described earlier. This is something entirely different. This is a slow, smooth, relentless increase, continuing year after year throughout the entire journey beyond the Heliopause. The sea is thickening around it. In a paper published in the journal Nature Astronomy in 2020, Don Gurnett and Bill Kurth of the University of Iowa presented this data showing that the density increase has been independently confirmed by 2 completely different measurement methods, the PLS instrument and the plasma wave instrument, PWS, on both Voyager 1 and Voyager 2. Not an instrument error, not a glitch. This is a real phenomenon. Interstellar space is becoming denser as Voyager 2 travels deeper into it. There are 3 competing hypotheses, and the scientific community has not yet been able to decide which one is correct. First, Voyager 2 is passing through compression waves from solar eruptions that occurred many years earlier and are only now reaching the edge of the solar system like piled-up ripples. Second, the solar system itself is moving through the galaxy and entering a region of higher plasma density, like a boat leaving a shallow bay into the deep ocean. Third, and the strangest, the Heliopause itself has a dynamic structure that has not been mapped, a phenomenon that all the models built from Earth are completely missing. There is an additional detail that makes these 3 hypotheses even more complicated. The Sun has an 11-year cycle. When it is active, the solar wind pushes harder and the heliosphere bubble inflates. When it is quiet, the bubble contracts. NASA uses a simple metaphor to describe this phenomenon. The Sun is breathing, and every time the Sun breathes, the outermost boundary of the solar system vibrates with it. One more detail. Temperature. Right at the Heliopause boundary, the PLS measured hot plasma from 30,000 to 50,000 Kelvin, far higher than the models predicted. Not a smooth transition, but a wall of hot plasma, higher density than predicted, higher temperature than predicted. 2 surprises at once, measured by the same 49-year-old instrument. The scientific community has no way to distinguish among the hypotheses without more data, more time, more survival of a machine that is nearly running out of power. Every year the PLS still runs is a year of precious data. Every year it shuts down is a year the questions remain open, and the window to answer them will close, possibly forever, or at least for a generation. Now pause for a moment and reflect on what you have just heard, because there is a truth that is very easy to overlook when you are focused on the numbers and the boundaries. The Heliopause that Voyager 2 has just crossed, the plasma bubble of our Sun, is not merely an academic concept for physicists to study, it is a shield, and that shield is protecting you right now. Interstellar space is not a benign environment. It is filled with cosmic rays, high-energy particles accelerated by supernova explosions that occurred thousands or millions of light years away. Supernovas that we ourselves may never know about, that died before our ancestors learned to walk upright. If those particles reached Earth at full intensity, they would destroy DNA. They would create cancer mutations in every living organism on this planet. On geological timescales, they would reshape the entire evolution of life in ways we do not even fully understand. But they do not arrive at full intensity. Here is the specific number I need you to remember. The Heliopause blocks about 70% of all galactic cosmic rays that would otherwise strike our solar system. 70%. In the graph that the PLS sent back on the day Voyager 2 crossed the boundary, you can see this with your own eyes. The moment the spacecraft stepped to the other side, the number of galactic cosmic rays jumped upward, while the number of heliospheric particles dropped dramatically, almost within the same hour. That is how you measure a shield, by going outside it and looking back. But there is a detail that the PLS detected afterward that makes everything more worrying. Voyager 2 measured 2 interstellar radiation pockets lying inside the Heliopause, inside the shield, in places where they should not have been able to exist. Radiation had leaked through. The shield has cracks that no model ever predicted. Now put the two things together. If the plasma density outside the Heliopause is increasing as I have described, the pressure pushing inward on the shield is increasing, and the shield may contract over time. If the shield has cracks, we are being exposed to more radiation than we think right at this moment. We do not know for certain what all of this means for life on Earth. The timescales are very long. Any changes that may occur will unfold over centuries or millennia, not over years or decades. But the fact that we can even ask that question, the fact that humanity has the data to begin thinking scientifically about its protective shield, all of it is thanks to a 4-watt machine drifting through the darkness 13 billion miles away. Without that shield, we would not be here. Without Voyager 2, we would not know how that shield is changing, and when the PLS finally stops working, our only window into understanding that boundary in real time will close. Now pause for a moment and talk about 2 moments in the journey of Voyager 2 when the spacecraft nearly vanished from the life of humanity. Not because of equipment failure, but because of something far more fragile, because of silence. The first moment began on July 25th, 2020. In Canberra, Australia, there is a giant antenna dish called DSS-43, 70 meters in diameter, weighing 3,000 tons. NASA's Deep Space Network consists of 3 stations in California, Madrid, and Canberra, placed 120 degrees apart around Earth, so that at least one station always has a view of a spacecraft. But Voyager 2 is in the southern sky, and on this entire planet, there is only one single antenna capable of sending commands to it, DSS-43, not one of many, the only one. That day, DSS-43 was shut down for a major upgrade lasting 8 months. And during those 8 months, Voyager 2 drifted in the darkness. It was still transmitting signals. The other antennas could still hear it, but no one could talk back. If Voyager 2 encountered a problem, the JPL team could only sit and watch. The 43-year-old machine 18 billion miles away was ordered to take care of itself. In March 2021, DSS-43 came back online. The first command sent to Voyager 2 was confirmed to have arrived. The spacecraft responded. It was still fine. But that was only the first time. The second moment occurred on July 21st, 2023, and this time it was almost the JPL team itself that caused it. A sequence of commands entered incorrectly caused Voyager 2 to tilt its antenna 2 degrees away from the direction of Earth. 2 degrees may sound small. At a distance of 19 billion kilometers, 2 degrees means the radio beam, already so weak that it is only a few attawatts when it reaches Earth, fainter than the light of a refrigerator light seen from the moon, was now sliding completely off our planet. Voyager 2 was still transmitting. It was just that no one could hear it. The spacecraft is programmed to automatically adjust its antenna back toward Earth, but the next automatic adjustment would not happen until October. The JPL team could not wait. On August 4th, 2023, DSN Canberra transmitted what the engineers call an interstellar shout, a scream into the darkness at the highest power the system could generate. The signal took 19 hours to reach Voyager 2, plus another 19 hours for any reply to return. 4 painful days of silence at JPL, 4 days when no one knew whether the machine could still hear. And then on August 8th, the signal returned. Voyager 2 had heard. It had corrected its antenna. It was still alive. The 46-year-old machine had forgiven the human error and continued its mission. Voyager 2 is not merely running out of power, it is surviving in an environment where every small mistake can be the endpoint. The machine is living thanks to the extremely careful attention of the team at JPL, people who are caring for it the way doctors care for an elderly patient they have followed for an entire career. And the machine is repaying that care by continuing to send back plasma measurements that nothing else in our civilization can make. In the brief hours when Voyager 2 crossed that boundary, the PLS recorded a detail I have not yet told you. A detail that took 7 years of analysis for the scientific community to understand its meaning. Remember the third hypothesis I mentioned earlier, the one I called an unmapped dynamic structure? This is the evidence for it. In the short time before crossing the Heliopause, the PLS measured an anomalous layer of hot, tightly compressed plasma lying right inside the boundary. The temperature was much higher than typical solar wind, the density was clearly higher. This was not ordinary slowing solar wind. This was an entirely new structure, a layer no one knew existed. Researchers at the University of Iowa and JPL have given this phenomenon the official name plasma boundary layer. It is about half an astronomical unit thick, equivalent to 75 million kilometers, a hidden cocoon layer between our home and the cold space outside. Earlier I called the Heliopause a single-layer shield. That is how we understood it for decades. But this cocoon layer tells us something different. The shield is not one layer, it is at least 2 layers, with a hot cushion in between. And that is not all. The PLS also detected something about the magnetic field at the boundary. Models had predicted that inside the Heliopause is the solar magnetic field, outside is the galactic magnetic field, and the two have significantly different directions. Voyager 2 discovered that the 2 magnetic fields have directions surprisingly similar, as if someone had arranged them, or as if they had been quietly communicating across millions of years. One more thing. Remember the 2 numbers I placed side by side when telling about the moment of crossing? Voyager 1 crossed at 119 astronomical units, Voyager 2 crossed at 121. A difference of 2 astronomical units after 6 years is not a coincidence. Classical models predicted the Heliopause as a perfect sphere surrounding the Sun. The reality revealed by the 2 Voyager spacecraft is completely different. The Heliopause has an uneven, wavy shape, wrinkled, asymmetric. It is not a static wall. It is a living body with its own rhythm. 3 discoveries, 1 4-watt machine, a hidden cocoon layer no one knew existed, 2 magnetic fields unexpectedly aligned, a wavy boundary that is not a sphere, all from an instrument assembled before Steve Jobs and Steve Wozniak put together the first Apple computer in a garage. Now let us talk about what is happening right now in 2026, because the story of Voyager 2 is entering a chapter that the JPL team has prepared for many years but no one actually wants to carry out. In March 2025, the LECP instrument on Voyager 2 was turned off after 48 years of uninterrupted operation. It did not fail, it simply no longer had enough power to run. The spacecraft runs on 3 radioisotope thermoelectric generators, each containing a block of plutonium-238 that decays and produces heat, which is converted into electricity. When Voyager 2 was launched in 1977, the 3 generators together produced 470 watts. Today they produce only about 250 watts, and each year they lose another 4 watts. They cannot be recharged, they cannot be replaced. The current estimate for the final death point is the early 2030s. On February 27, 2026, Voyager 1 encountered an alarming electrical anomaly during a routine roll maneuver. The power level dropped suddenly and nearly triggered the automatic low-voltage protection system. The JPL team had to decide quickly. On April 17, 2026, they turned off the LEACP on Voyager 1 to save the spacecraft, but there is a much longer-term plan being prepared. It has the internal name, the Big Bang. The idea is this. Instead of turning off instruments one by one as power gradually runs out, the JPL team will simultaneously swap multiple power-consuming components, replace them with less power-hungry options, and redistribute the electrical flow through the systems in a way no one has ever tried on an operating spacecraft after 4 decades. The risk is real, there is no undo button, and Voyager 2 will go first. Voyager 2 will be the guinea pig, because it has a little more power in reserve, is a little closer to Earth, and if something goes wrong, the consequences will be less catastrophic than testing on Voyager 1. In May and June 2026, the JPL team will send the Big Bang commands to Voyager 2. Each command will take 19 hours 43 minutes to arrive, and another 19 hours 43 minutes for any reply to return, nearly 2 days to complete a single communication loop. If something goes wrong, the damage will already have lasted nearly 2 days before anyone knows. But if the Big Bang succeeds on Voyager 2, the same procedure will be tried on Voyager 1 no earlier than July 2026. And if the Big Bang succeeds on Voyager 1, there is a real possibility that the LECP turned off in April could be turned back on. The partially blinded spacecraft could regain one of its eyes. Voyager 2 is the guinea pig to save its sibling. There is no dramatic announcement from NASA, only the quiet engineering team in Pasadena, preparing to send commands that will reach a machine that has flown farther than any object humanity has ever built, except one, and asking it to accept the risks so that the remaining machine can live longer. And there is one more milestone on the calendar that I want you to notice. August 20th, 2026, only a few weeks after the Big Bang is tested on Voyager 1, Voyager 2 will celebrate exactly 49 years of uninterrupted operation. The machine, designed to live 5 years, will turn 49 years old on that day, only a few weeks after the largest surgery of its life. Now look farther. Look much farther. Farther than 2030, when the generators of Voyager 2 will finally no longer have enough power to run any scientific instrument. Farther than this century, farther than this millennium. Because Voyager 2 will not stop. There is no friction in interstellar space. There is no atmosphere to slow it down. It is moving at about 57,000 kilometers per hour, and it will continue moving like that for millions of years. Unlike Voyager 1, which has a trajectory generally toward the constellation Ophiuchus with no specific destination, Voyager 2 has an appointment. In about 40,000 years, it will pass within 1.7 light-years of a star named Ross 248, a small red dwarf in the constellation Andromeda. 40,000 years is a long time. 40,000 years ago, our ancestors were painting horses and bison on the walls of Chauvet Cave in southern France. After that, Voyager 2 will keep going. In about 296,000 years, it will pass the star Sirius, the brightest star in our night sky. 300,000 years is longer than the entire history of modern Homo sapiens. When Voyager 2 nears Sirius, nothing that humans have ever built will still exist in any recognizable form, but the spacecraft will still be there, silent, carrying the golden record. On the record, there are greetings in 55 languages. There are the sounds of ocean waves, wind, rain falling in a forest, the laughter and crying of children, 90 minutes of music from cultures across history. There is a map showing the position of the Sun relative to 14 pulsar stars, so that anyone who finds the record can determine exactly where we came from. On the record is also the brainwave recording of Anne Druin, the Golden Record's editor, measured while she was thinking about love and hope and questions about the future. Carl Sagan called it a message in a bottle thrown into the cosmic ocean. Because whoever finally finds Voyager 2, whether another civilization in a million years or a form of intelligence we cannot even imagine, the record will tell them something true, that there was a species here, that they were curious, that they reached out. The record will still be moving when the Sun has become a red giant and swallowed Earth's orbit about 5 billion years from now. It will still be moving after every human city, every archive, every piece of stone we ever carved a name into has been erased by geology and time. It is the most eternal thing our civilization has ever created, and it is riding on a 4-watt machine about to undergo the largest surgery of its life. This is what I want you to take with you when this video ends. Right now, the only plasma instrument humanity has ever placed into interstellar space with the ability to directly measure the density and temperature of the surrounding environment is mounted on a 49-year-old machine. That machine runs on 4 watts of electricity, less than the light above the kitchen sink in your house. It is 13 billion miles away. Every command to it takes 19 hours, 43 minutes. And in the coming weeks, it will undergo a procedure never before tried on any operating spacecraft at this distance, with no undo button, no manual override. We have built things much larger. We have built things much more powerful. We have built things that cost many more billions of dollars and include far more complex technology, and none of them can tell us what Voyager 2 is telling us right now, because none of them had the boldness to keep going long enough to actually get there with a plasma instrument still working. There are questions about the universe that can only be answered from inside the universe, not from telescopes on the ground, not from satellites in Earth orbit, only from a machine that has crossed the boundary. If Voyager 2 survives the Big Bang, we gain another year to listen. If not, humanity's only window into interstellar space will close sooner, and the next generation will have to build a new mission that could take 25 or 30 years just to reach the place where Voyager 2 is right now. A 4-watt machine. A plasma instrument still working. A sea that is thickening. A chance to listen. The question is whether anyone is paying attention. If you came here for this kind of story, subscribe now and turn on notifications, because next time we will go deeper into the edge of what science truly knows. Leave a comment with what surprised you most in this video, and share it with someone who needs to hear it, because the story of Voyager 2 deserves more than the silence it is receiving.